All right, so hello and welcome everyone to week six. Sorry, to week six of interactive live sessions for the course on fundamentals of convective heat transfer. It is being offered by NPTEL and it is being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras and I'm the PMRF TA for this course. And like every other week, we shall be solving some problems together and discussing anything and everything related to the course. So, we are almost halfway through the entire course. It's a 12-week course, and today is week six. So, without further ado, we will now get started with question number one of today's session, which is asking us to consider the following statements. And after reading the three statements, we have to pick out which ones are correct. And there are some combinations given in the options below. We have to pick out the correct option from there. Now, read the entire question carefully and figure out the solution. And once you have done so, you can either type it in the chat box or you can unmute and answer as you feel comfortable. Uh, if you have any doubts related to the question or anything else, please make sure that you clarify it. Okay, no need to hesitate. So these are interactive sessions. We will try to keep them as much interactive as possible. So back to the question now. We have three statements. Statement number one says that for Prandtl number comparable with 1, both velocity and thermal boundary layer develop almost at the same rate. For wait a second, are these the right slides? I'm not sure. Sorry, I got the wrong slides. Give me a moment. Uh, those were the same questions as you saw in the assignment, I believe. Okay, what happened? Please hold on for some time. I'll try to get the right slides. Also. Today is week 6. This was the one. Okay, let me share this one. Please hang on, there's been an issue. I'm trying to fix it. Yeah, got it. Yeah, got it now. And now I'm sharing the screen. Should be visible. Are my slides visible? They're visible, right? Okay. So sorry for the issue. I will get started once again. So this is question number one. Read this carefully and try to figure out the solution. And once you have done so, you can either type it in the chat box or you can unmute and answer as well. So this is question number one for today's session, which has given us three statements, and we have to pick out the correct one and then choose the correct combinations from the four options given below. So question number one is for Prandtl number comparable to 1, both velocity and thermal boundary layer develop at almost the same rate. For statement number 2 says for Prandtl number approximately 1, the thermal boundary layer will develop at a very slow rate, whereas the velocity profile will already be fully developed. And statement 3 says for Prandtl number close to 1, the temperature boundary layer or the thermal boundary layer will develop so rapidly that the velocity profile may be assumed to be almost uniform. That is a plug flow. So you have to choose the correct options among these. So is it option A, only statement 1 and 2 are correct? Option B, only statement 1 is correct? Option C, only statement 3 is correct? Or option D, all of the three statements are correct? We have one quick response, that is option B, only one is correct. Let's see what others have to say. So we have one response in favor of option B. I'd request everyone to participate in this and put in your responses. There's no hurry. Try to, read everything properly and then pick your option. So there's one response in favor of option C, and someone says 2 and 3 are correct, and 1 is correct within boundary layer. These are all related to the boundary layer only. It is related to the growth of the boundary layer. How will it grow? So velocity profile being fully developed or being uniform means either the uh, boundary layer will grow or grow rapidly, or it will not grow rapidly. If it grows, then the velocity profile will be fully developed, and if not, it will be almost uniform. Someone else says option B as well. Let's see what others have to say. So statement 1 says that for Prandtl number approximately 1, which means that the uh, momentum diffusivity is almost equal, or at least of the same order as the thermal diffusivity. So in that case, whether both the hydrodynamic as well as thermal boundary layer develop almost at the same rate, or does the thermal boundary layer develop at a slow rate whereas the hydrodynamic boundary layer grows at a very high rate, or is it that the thermal boundary layer develops rapidly and the velocity boundary layer develops uh, much slower compared to that? We have another response in favor of option B. Okay, so let's have a look at the solution. The solution is option B, only one is correct because see, so Prandtl number being comparable to 1 means that delta by del t. So this is proportionate to, or not exactly proportionate to, but this is a function of the Prandtl number, right? So this to the power 1/3, I guess, is Prandtl number. So delta x, both are functions of x, mind you. So this being all approximately 1 means this will also be approximately 1. So the thermal boundary layer as well as the hydrodynamic boundary layer, they will develop at almost the same rate. They will remain comparable to each other. Now, if let's say Prandtl number was much less than 1, meaning that the alpha was much greater than nu, then that would mean that the thermal boundary layer would grow rapidly. So much more rapidly than the hydrodynamic boundary layer, which means the flow will be thermally developed before it is hydrodynamically developed. So this third case is corresponding to Prandtl number much less than 1, and the other case where the thermal boundary layer does not develop rapidly but the hydrodynamic boundary layer develops rapidly, that is that corresponds to Prandtl number much greater than 1 case, where the viscosity is much higher than thermal diffusivity. Does it make sense what I just said? You get the reasoning, right? Any questions on this? So this reasoning is clear, right? How,
Yes, sir.
yeah. Yes, you had to say something. Uh, did you have anything to say?
No, sir.
Okay, so this thing became clear, right? So depending on Prandtl number, we can predict which of the boundary layers will grow faster than the other.
Yes, sir. Yes.
Makes sense, right? Okay. Any other questions? Okay, so if there are no questions, we will move along. We'll move on to question number 2, which is asking us, in the thermally and hydrodynamically fully developed flow of a fluid with constant properties, in an isothermal circular duct, the wall heat flux varies linearly with x. Does it increase exponentially with x? Is it independent of x? Or does it decrease exponentially with x? So we have a circular duct and a fully developed flow profile, both hydrodynamically and thermally. And it's an isothermal circular duct, meaning the boundary condition is constant temperature boundary condition. So in that case, the wall heat flux, or QW double prime, as we have been calling it, what kind of a function of x is it? Does it vary linearly with x? Is it does it increase exponentially with x? Does it is it independent of x, or does it decrease exponentially with x? So QW is a function of x. What kind of a function of x is the question. Okay, so we have one response saying linearly, that is option A. Let's see what others have to say. Option D decreases linearly with x. So we have two responses so far. Let's see what others have to say. We have one response saying that Q varies linearly with x, and another one saying that it decreases exponentially with x. We have another supporter of option A, that is, it varies linearly with x. Okay, so let's have a look at the solution. The solution is actually option D. So whoever said so, you are right. So it decreases exponentially with x. Now, why is that? Let's try to sorry. So let's try to recapitulate from previous class how the temperature varied. So the temperature of the wall, it is constant. So here I have T, and on the x-axis I have the actual dimension x. So let's say a cold fluid enters the sorry. So let's say a cold fluid enters this. Initially, the temperature difference is high, so the wall heat flux will also be high, and it will rapidly try to approach towards this. Now, as the temperature difference becomes smaller, the heat flux will also become smaller, and the rate of increase of this T, or the rate of decrease of the temperature difference, this will also slow down. As a result, it will give this exponential nature of Tm, or the bulk mean temperature. So uh, this decrease in temperature is exponential, equal to something, some, not alpha, like some beta x. There was some, that was some function of the perimeter area, the mass flow rate, and the flow properties, and so on. So this delta T was proportionate to this, and Q, as we know, is proportionate to this delta T. And since this is a uh, function which decreases exponentially with x, Q will also decrease exponentially with x. Here beta is some constant, don't worry about it. But the nature of Q, or Q double prime wall, the wall heat flux, this is uh, this decreases exponentially with x. So both option B and D said that the nature would be exponential, but B said it would increase exponentially, which is not true. It would decrease because the temperature difference, as you can see here, is decreasing with x. So the wall heat flux will also decrease with x. And mathematically, we have this negative sign over here. That's why the wall heat flux will decrease exponentially with x. Does it make sense?
Yes, sir.
Okay. Any questions regarding this? So it does not vary linearly with x, right? You got the point, huh? Yes. You can unmute and answer. Okay. I think that was my mistake. Anyway, if you have a question, please don't hesitate. Okay, cool. So we will move along. We will move on to question number 3 of today's session, which is asking us that for uniform heat flux condition, the value of Nusselt number for hydrodynamically and thermally developed flow in a circular duct is what? So we saw this in one of the lectures in week 6, that for a fully developed hydrodynamically as well as thermally developed flow in a circular duct, uh, what was the value of the Nusselt number? And Nusselt number with respect to d, the diameter of the circular duct. And this is a isothermal case. So, oh, sorry, not isothermal, but uniform heat flux case, where Q is constant. What was the value of Nusselt number for this case? Was it option A 4.36, which someone already says that it is? Then option B 3.66, option C 4.027, or is it option D? Sorry, what happened here? Or option D 4.76. 4.36, 3.66, 4.027, or is it 4.76? Okay, we have two more responses in favor of option A. Let's see what others have to say. We got three quick responses. I'm expecting some more. Yeah. So this one number is what is important for us. We already saw in the lectures how difficult it was to finally get to this number. Like the process was analytical process only, but the math was really involved and very difficult, to be honest. It's not something that we want to repeat time and again, but then again, uh, knowing it is important, since we get the feel that why it is so. What is happening to this? Anyway, we will move on to the next question. We will have a look at the solution. And the solution is indeed option A, 4.36. So, there's nothing to say here. This is what the result is from an analytical solution of a fully developed flow through a circular duct. Oh, no. The sharing stopped, right? I'll share again. Right. Yeah, sure. Yeah.
Sir, I just want to make it clear that you are going to just discuss the questions here and their answers. Or I have one question. I have raised one question in the discussion forum.
Oh, okay.
So we leave the
There are
answer.
actually different people who handle the discussion forum, but I can also access that and go over there. And if you want to ask questions, you can ask them over here as well.
Okay, sir. So at the end, I will ask her, or
Okay.
so that you will not be interrupted. At the end, I will ask you, sir.
With no problem with interrupting me. Like we are here to discuss only, and my device is heavily malfunctioning.
Okay, okay. So may I raise here?
This is one. Okay. I'll share from here. Give me a moment. I'll share my screen. Then you can ask. Just a moment.
Okay, sir. Okay.
Every day a new problem. Last day my writing device wasn't working properly. Today my laptop itself is malfunctioning. Week 6. Drop it here. Yeah, there were some issues with my voice as well. I understand my laptop is not working well. I hope now you can see my screen and hear me and see my slides as well, right?
Yes, yes.
Okay, cool. So we will go down to the slide that we were in. We were here, I guess. Yeah. Okay, so you can ask your question now.
Sir, in the have you seen any kind of the water cooler, sir?
Water cooler, like the ones that we use in North India, like where you put in water and there's a fan running, that one, right? Or
No, no, no. The drinking water cooler, sir. In
oh,
the
water
college
cooler.
premises, we are having
Yeah, yeah.
it
Oh,
stores around
okay, got it.
40 liters of
Hmm. So
40
you
liters of
topple
water.
the water can over and it gets cooled and you can fill your bottles. That one, right?
Yes, yes, yes. In the college premises, we are having.
Okay.
So my question is, in the water tank,
Hmm.
so when the refrigerant is passing around it, there is no physical contact with the water. So how to calculate the heat transfer in a stored water tank? Or else we can use the same like natural convection analogy, and we can calculate. Or how is there any method to calculate the heat transfer in the stored water, because it's not air and it's not flowing.
Yeah. So yeah, first, yeah. So what happens
Is there
with
any
that
method
kind of
in
a thing is that we put a can above, and there's this storage tank below, which has usually they have three separate tanks, right? One is for hot, one is for normal, and one is for cool. So
no, no,
sort
sir.
of
I'm not asking that water tank, sir,
then
because there's the water quantity is lesser, max 20 liters capacity. But if you consider a ice tank, or if you consider a tank where 80 liters of water is stored,
so basically one tank where cold water is there, right?
huh, and
So
which is actually hot water and it is cooled by the refrigerant.
cooled by the refrigerant. Okay, so we have a cooling coil like this here, which is taking away heat from this water and cooling it.
Yes, but the cooling coil is not in physical contact, sir.
Without being physically in contact with water, how will it cool it? There has to be some point where
No, no, sir.
yeah,
In that tank of the wall of the tank is connected with the refrigerant tube,
yeah.
which is
So
placed there.
even if the cooling coil is not in contact, there will be these walls near the tube, which will
Huh, cool it.
yeah.
So how to analyze this heat transfer in that water?
Okay, so it's very similar to what we are doing. Yeah, so something like this. So the cooling coils are around this wall. These walls become at a temperature which is less than the okay. So TW meaning wall, and uh, I'll call this T liquid maybe, which is the temperature of the liquid inside. So
Yes, yes, sir.
so these walls are in contact with the liquid, and here there will be natural convection setup. There's no forced convection
Yes,
here, you are right. So it will be very
yes, sir, yes,
similar
sir.
to one very cold wall and some hot liquid near it. So there, the liquid just in contact with the wall that will cool down, become dense, and try to move down. So there will be a boundary layer set up like this, where the flow velocity will be something like this. So yeah, so the velocities will be something like this, and so this is u versus, let's say, this direction being x, and the thermal profile will also be lesser near the wall, and it will be higher as it approaches the liquid. So it will be something like this and become constant outside the boundary layer. This is temperature. So once we study natural convection, you can get a better feel of these things. But yeah, you're right. So there will be no forced convection. There will be only natural convection within the liquid present in the tank. Does that answer your question?
Yes, sir. Yes, yes. I got it, sir. Thank you, sir. Thank you, sir.
Okay, no problem. So we will move along. We move on to question number 4 of today's session, which is now asking us that for uniform wall temperature condition, the value of Nusselt number for hydrodynamically and thermally developed flow in a circular duct is what? So previously we saw for a uniform surface temperature, surface heat flux condition, what was the Nusselt number. Now we have to find it out for an isothermal wall, for uniform wall temperature condition. Is it option A 3.614, option B 4.021, option C 3.66, or is it option D 4.36? Previously we saw that for uniform surface heat flux it was 4.36. What will be the case for uniform wall temperature? Okay, we have multiple quick responses, all in favor of option C. So we have 4 responses so far in favor of option C. Let's see what others have to say. How many are present now? I'm glad that you guys are not leaving after all these technical malfunction every day. Okay, another one in favor of option C. Okay, so option C seems to be the popular choice. We will have a look, and it is indeed the correct answer. So for isothermal uh, circular duct and fully developed flow, both hydrodynamically and thermally, the Nusselt number with respect to the diameter d is equal to 3.66. I hope there are no questions regarding this one. We will move along. Okay, so the temperature slope for uniform wall temperature at the wall is lower than the temperature slope for uniform wall heat flux. Is it true or is it false? So the statement is that for uh, 2 cases where I have a constant heat flux, Q double dot equal to constant, and another case where I have T constant, which is TW equal to constant, the isothermal wall case. So in these 2 cases, they are saying that for the uniform wall temperature case, the temperature slope is lower than the temperature slope for the uniform wall heat flux. Is it true or is it false? Now remember, temperature slope is directly connected to the magnitude of heat flux. If it is more, then the heat flux will be more. If it is less, then the heat flux will be less. Like that. Okay, so we have one response saying it's false. Let's see what others have to say. Another one says A, that is true. We already have the crowd divided. Okay, 2 more responses in favor of true. Question number 5 of today's session is asking us that the temperature slope for uniform wall temperature at wall is lower than the temperature slope for uniform wall heat flux. Is this statement true or is it false? Another one says it's false. Pretty divided crowd on this one. Okay, so now we will have a look at the solution. The solution is actually A, true. So what happens if we solve for the temperature profile for the uniform wall heat flux case, we get a perfectly parabolic shape like this. This is temperature. This is for Q double prime equal to constant. And for the other case where TW equal to constant, we get a profile which is somewhat like this. So a lot of the fluid near the wall is actually uh, very near the temperature of the wall itself. So this is what the profile looks like. So as you can see, the slope here is much lesser than the slope here. So that's why uh, this statement is true. It comes from the solution of the temperature profile. Does it make sense? Any questions on this? No? Okay. So hoping things are clear, we will move along. We will move along to question number 6, which is now a numerical type question, which is asking us that the increase in heat transfer in case of uniform wall heat flux boundary condition compared to uniform wall temperature condition is blank percentage. You have to find out this number. So if we go from uniform wall temperature to uniform heat flux, there will be an increase in the heat transfer. What will that percentage increase be? So in this case, you can assume the other things like the temperature difference, the area, the geometry, and all to be same. I'll give you a hint. So in the previous questions, we saw what the Nusselt number is for these two different cases. The answer to the uh, increase in heat transfer or the percentage increase in heat transfer lies within the Nusselt number, which is directly proportional to the heat transfer coefficient and therefore the actual rate of heat transfer. Okay, so we have one response saying it's 16%. Let's see what others have to say. Another response saying it's 19.2. Okay, we will try to solve this. So this case, this uniform wall temperature case, we will call this 1 because we are comparing it with this, and the increased one due to uniform heat flux condition, we will call this Nusselt number 2. So in the previous cases, where in the previous questions, we saw that for uniform wall temperature condition, it was 3.66, and the other case that for uniform surface heat flux, it was 4.36. So in Nusselt number 1 was 3.66 and Nusselt number 2 becomes 4.36. So this percentage increase would be Nu2 minus Nu1 divided by Nu1 into 100%. Right. So this is 4.36 minus 3.66 divided by 3.66 into 100%. So this difference will be like zero point 0.7, I believe. Yeah, zero point 0.7 into 100, that is uh, 70 divided by 3.66%. What is 70 divided by 3.66? It's 19.125. So whoever said 19.12, you are absolutely correct. Does it make sense? Any questions? So the person who got 16%, you took Nu2 in the denominator, right? Yeah. So here, here the language of the question is of importance. It says that compared to uniform wall temperature condition. So it's the uniform wall temperature condition which has to be the reference point for this, and there is an increase from that reference point.
Compared to means we have to take like a uniform wall flux boundary condition, right?
Yeah, so the idea is that what how much is B greater than A compared to A? How will we do that? We will do B minus A divided by A, right? A is our baseline flux.
Okay, sir.
Okay, so it is increasing from A to become B.
Okay, sir.
Okay, all right. So, uh, are there any other questions regarding this one? Anyone else? Any questions? No? Okay. So then we will move along. Uh, we'll move on to question number 7 of today's session, which is asking us that the heat flux through walls of two parallel plates with hydraulic diameter d is uniform q double prime. So it's a uniform heat flux condition between two parallel plates. The flow regime is laminar. The velocity and temperature profiles are fully developed. So for this case, calculate the value of Nusselt number based on hydraulic diameter. So the question is clear, right? We have a parallel plate like this. There is a uniform heat flux Q double prime through both plates. The hydraulic diameter is capital D, and we have to find out the Nusselt number with respect to D. I'll give one more hint over here. The hydraulic diameter is nothing but 4 into area divided by the perimeter of any cross section. You don't have to solve for this. This was solved in class. You can, I guess, go back and try to recapitulate what was the answer there. Understanding the case is important. The case is this one, where we have a uniform heat flux condition and a fully developed flow. So the flow profile is parabolic, and the thermal profile is also fully developed. Arrow won't be there, sorry. This is the temperature profile, this is the velocity profile. Yeah. So it's a simple question. You can go back to your notes and try to find it out. Nusselt number in all cases is actually derived based on hydraulic diameter itself. So if it's a circular tube, then the diameter and the hydraulic diameter is the same thing. But for any cross section that is not a circle, we always try to do things in reference to the hydraulic diameter, be it the finding the Reynolds number or the Prandtl number, not Prandtl number, or the Nusselt number, things like that. So that maintains a sort of uniformity across different cross sections as well. Okay, so we have started to get responses. All look like 8.21, 8.23, 8.234. Yeah, correct. All of you are right. So in this case, the Nusselt number actually boils down to 8. The actual thing was something like 140 by 17. If we now try to do this, it will be something like 8.23 dot dot dot. Yeah, and the hydraulic diameter in this case is what, 4 into, let's say, if this distance is h in from the center line towards both the walls, so the area would be 4 into h and perimeter would be 2. Now this is like width being the same in both cases, so width cancels out, 2 cancels out, so d equal to 2h, that is the uh, hydraulic diameter, and so this Nusselt number is with respect to 2h in this case. Okay, if there are no problems regarding this, if anyone has any question, you can ask. No? Okay, in that case, we will keep rolling. We'll move on to question number 8, which is asking us that for a hydrodynamically and a thermally developed flow through parallel plate channel, once again, the decrease in heat transfer in case of uniform wall temperature in comparison to uniform heat flux taken with respect to uniform wall temperature is what? So it's similar to something that we did earlier, but in this case, you remember that it's for a parallel plate channel and not a circular duct, which we actually looked into detail in 3 questions of today's session. Parallel plates were taught in lecture 2, I guess, right? I also forgot the Nusselt numbers. So we just now saw that for uniform wall heat flux, it was 8.235 or 140 by 17. And we have to look for the one where it was uniform surface temperature or uniform wall temperature. So the solution of that was pretty involved. And I guess we finally got uh, this equal to 7.536. Okay. Okay, so let's see if someone can help me with the numbers. First of all, I need, okay, so for this case, in comparison to uniform heat flux, so this is now our base case, Nusselt number 1. And the uniform wall temperature case is the modified one. So Nusselt number 1, uniform heat flux, as we saw in the previous answer, it is equal to 140 by 17 or 8.23. And for constant wall temperature, what was this equal to? 7 point something, right? I'll have a look
And
at the
7.54.
7.536, something like that. Yeah, 7.53, we will go with that. 7.53. So now this percentage decrease would be a negative one. So it will be NU1 minus NU2 divided by NU1 into 100%. So NU1 is 8.23 minus 7.53 divided by 8.23 again into 100%. So 8.23 minus 7.53, this is how much? Again, zero point 0.7. These differences turn out to be 0.7 every time. Anyway, this is just by coincidence, and it's not that every time it will be 0.7. So now 70 by 8.23, how much is that? Somewhat 8.5%. Is everyone else getting the same answer? Okay, both of two of you wrote 9.283 or no, okay, single person wrote it twice. 9.283. Uh, so did you take 7.53 in the denominator in that case? 70 by 7.53. Yeah, right. So once again, it's English language rather than convective heat transfer, which is fooling us. So you have to remember what is it in comparison to. So here in this case, it was in comparison to uniform heat flux condition, which gave us an Nusselt number of 8.23. So that's why we have to divide it with that. Okay. Any other questions regarding this thing? Makes sense, right? You all are comfortable with questions like these because you can expect them in future assignments or even the final exam.
Yes, sir.
Okay.
Sir, can you please go back to question 6 and explain another?
Question 6. Okay, we will go back. Question 6. Yeah. So in case the increase in heat transfer in case of uniform heat flux boundary condition compared to uniform wall temperature condition is what percentage? So for uniform wall temperature condition, we found out that Nusselt number is 3.66, and for uniform heat flux condition, the Nusselt number was 4.36. So now we have to find this percentage increase, which is given by this formula, the Nusselt number 2 minus the Nusselt number 1 divided by Nusselt number 1, the one that we are comparing it against. So that's why now after this it's just simple math. We plug in all the numbers and try to find out what that percentage is.
Sir, but when I looked into that lecture notes, but in that only it's showing 16%.
Your voice is breaking up. I'm sorry, I couldn't understand your question.
Sir, in the lecture notes, it's showing 16% only, sir, for the same question.
Where is it showing
It's in there,
16%?
sir. In lecture notes number 4, I think, sir. In week 6, fourth
Yeah.
lecture notes.
Okay, I'll try.
Last slide.
Okay, I'll try to open it up. It's lecture
Okay,
4,
sir.
is it?
The lecture notes 4, sir, in the week 6.
In week 6, lecture 4. Okay, I'm opening it up. Maybe I'll share the screen as well. Wait.
Okay.
Uh, yeah, my screen is visible, right? So this is lecture 4 of week 6. Let's see. Towards the end, you said, right?
Yes, sir.
So Nusselt number 3.66, 4.36, the temperature slope, so and so. There is almost 16% increase in heat transfer in case of uniform heat flux compared to uniform wall temperature. Okay, so maybe this is where you got the answer, but you get my point, right? Why it is not 16%, but rather what we calculated, like from 3.66, from uniform wall temperature condition. If we go
Okay, sir.
to uniform wall heat flux, what is the percentage increase? So my baseline is the uniform temperature case, and the heat flux case is the increased case. So we really have to compare it with the baseline case, right? Whatever the difference is, the difference won't change. It
Okay,
is
sir.
the denominator that changes
Okay.
on which way we are thinking. So yeah, I
Okay, sir.
disagree with whatever is written in the lecture notes. Maybe we can ask Professor Dalal to, come in one of the live sessions and clarify.
Then it's supposed.
Yeah.
Yeah. Hi. Yes, sir. Yes, sir. Yes, sir.
Okay. Yeah. Tell me. You were saying something.
Yeah, it's okay, sir. If it is the answer, then we can move with this one.
Yeah.
Okay.
Okay. So
Yes.
the instructor sometimes do come for some live sessions, not regularly as we do, but when he comes, we can
Okay.
ask him this. Okay. And there was some other issue
Okay.
raised by someone else that there were a few
Oh,
wrong solutions given in the for the assignments, right?
yes, sir.
Yeah, I have informed
Yes,
that
sir.
to the NPTEL team, so they should correct it
Okay,
anytime.
sir.
Okay.
Okay, sir. Thank you, sir.
Okay, so I'll now get back to sharing this thing. What was it? Yeah. Okay. Any other question, anyone? So we were down to question 8. We will now move on to uh, which is again question 8. Sorry. So this this should have been question 9. Yeah. This is question 9 of today's session, which is now asking us that water is heated as it flows through a stack of parallel metallic blades. The blade to blade spacing is d equal to 1 centimeter, and the mean velocity through each channel is u equal to 3.2 centimeter per second. Each blade is heated electrically so that the two sides of the blade together release this much heat into the water. Assuming that the flow is laminar and water properties can be evaluated at 50 degrees Celsius, for flow to be thermally fully developed, what should be the length of the channel? So basically what we are asking is what is LT equal to, the thermal entry length. And what are the informations given? The informations given is that this is a uniform wall heat flux condition with Q double prime equal to 1600 watt per meter squared, and our U is 3.2 centimeter per second, so it's basically 3.2 into 10 to the power minus 2 meters per second, and this spacing D is equal to 1 centimeter or 0.01 meters. We have to find the entry length in meters as well. So it's better to convert everything else to the their SI units. And we are told that the water properties can be evaluated at 50 degrees Celsius. So I'll give some additional information. So the Prandtl number of water at 50 degrees Celsius is 3.56. At room temperature, it is close to 7, something like 6.9 or something. But at an elevated temperature of 50 degrees Celsius, it becomes close to 3.56. So you have to use all this to find out the entry length. So we have seen the formula for entry length earlier. You can use that and try to calculate it. Take your time, try to figure out the solution. It's simply a matter of using the right formula and doing the math correctly. Okay, we have one response saying it's 0.7. 0.7 meters? That should be pretty long, right? Anyway, it could be. I don't know. 8.2. Okay, 8.2 meters. That's even longer. Anyway, it could be. I'm not sure. We'll have to solve and see. Okay, so let's get started. So we know that uh, LT by D is equal to the entry length coefficient multiplied by Reynolds number and Prandtl number. Okay, no, we have to use the hydraulic diameter here. So the spacing is 1 centimeter. So what will be the hydraulic diameter? 4 into area. Area is D, and perimeter is 2, I guess, right? So this will be 2D or 0.02. Then we have to find out the Reynolds number. Okay, so we have the velocity. So this is u dh by nu. We will need this value as well for water. I'll look it up. 1 second. So this is 3.2 into 10 to the power minus 2. This is 0.02. Did someone look for the value of the kinematic viscosity of water at 50 degrees Celsius? Can you help me with the number? Okay, I'll quickly do a Google search of this. Kinematic viscosity of water. There is this very nice tool or a website known as the engineering toolbox, which really gives all these data very uh, you know concisely and very nicely. So we can use that. So at 50 degrees Celsius, I'm saying that the kinematic viscosity is 0.55 into 10 to the power minus 6. So we will use that value, 0.55 into 10 to the power minus 6. 0.55 into 10 to the power minus 6. So finally, what do we get? Quickly do this calculation. So 3.2. Okay, let me make sure we're doing this properly. So this becomes 10 to the power 4. So 3.2 multiplied by 0.02 into 10 power 4 is 640, and 640 divided by 0.55 is something close to 1200, so 1163. We already have Prandtl number 0.356, so now it's a matter of putting everything in. And CT for parallel plates is 0.012 multiplied by Reynolds number 1163. and Prandtl number 3.56. So what will I get if I multiply this? This multiplied by 0.12, no, 0.012, 0.012 and 3.56. Okay, I'm getting a very high number, which is 49.7 meters. Wow. Oh, okay, no, sorry. We have the hydraulic diameter here as well. Sorry. So this is LT by DH. LT would be this 49.7 multiplied by the hydraulic diameter, which is 0.02. It becomes 0.99. Yeah, so this is what I got. This is close to 1 meter. Anyway, the numbers don't matter, it's the process which is more important. So, any questions regarding this one? No? Okay, so I guess this was our last problem today. Thank you all for bearing with me, and happy Teachers Day to all of you. I'm sure in other classes we had some professors who are joining the course to refresh their knowledge, and even without them, every one of you is a teacher in your own right. So happy Teachers Day to all of you, and thank you for joining. We'll meet
Happy
again.
Teachers Day to you too, sir.
Thank you. Okay, so we will meet again next week. Thank you. Good night.
Thank you, sir. Thank you, sir. Good night.